temperature distribution in the conducting sheet. We have a thin metal sheet with a thickness of 1 millimeter. The potential difference is applied to the two sides of the sheet. Our task is to calculate the current value, the Joule heat power, and the temperature of the sheet. Since the sheet is thin, I'm going to use two-dimensional DC conduction problem to calculate the current density distribution, but for thermal analysis, I'm going to use the three-dimensional steady-state heat transfer problem. Okay, let's start QuickField now. In QuickField, I create new problem. Conductor. Next. Problem type is DC conduction. Plate thickness is 1 millimeter. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right is the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I'm going to draw it from scratch. First, I'm going to insert a rectangle with the dimensions 70 by 40 millimeters. Insert, and another rectangle with the dimensions 30 by 20 millimeters. Insert. Close. Zoom to fit. Now here I should switch to insert mode and add arcs. And I'd better to adjust the grid settings. 10 millimeters. Switch to select mode and select and remove unnecessary parts. Now this is the geometry model. Now let's assign labels. Through labels we can distinguish geometric objects and provide material properties. Switch to select objects mode, click the object to select and type in the label name here. This is conductor. This is grounded electrode, and this is the electric potential electrode. Now let's provide physical properties for these labels. Double-click the label name in the tree. The grounded electrode has 0 electric potential. The voltage electrode electric potential is 0.02 volts, and for the conductor I specify electrical conductivity, which is 1 megasiemens per meter. Okay, before I start the analysis, I should build the finite element mesh. Just press this button and the mesh will be generated. Now save all problem files and solve the problem. Let's take a look at the results. You can see the current density distribution, and it is not uniform. So is Joule heat distribution is not uniform as well. So I might expect to get non-uniform temperature distribution. Let's calculate the temperature distribution. I create new problem, conductor temperature. Next. Problem type is steady-state heat transfer. The plate is thin, so it was possible to simulate electric problem as a two-dimensional one, but for the thermal analysis, I need a 3D model. The model class is 3D extrusion, and to save time on geometry model creation, I'm going to reuse the geometry model file. So I click Browse button and look for conductor.mod. Here it is. Finish. To create a three-dimensional model from this plain sketch, I should assign levels to the objects. Click to select. Here you can see the levels 0 and 1000 millimeters. In fact, the conductive thickness is only 1 millimeter. So I type here 1. Now I can toggle two-dimensional, three-dimensional view. And here you can see the three-dimensional model. Here again I should assign labels. Click to select and the face is selected. To select the body, I should click the selected face again. Now the body is selected. This is the conductor, and thermal conductivity of the conductor is 50 watts per Kelvin meter. Okay. Now this conductor is cooled on all faces, all but the conducting faces, cooled by the air. So for these faces, for all these faces, all but the conducting faces, I should assign the convection boundary condition. Faces, convection. Ambient air temperature is 0 degrees and the convection coefficient is 10. Okay. These labels were used in electric problem. I do not need these labels here, so I just double click and do not specify any properties here and click OK. So now you see the 0 mark next to the label name. That means that this label doesn't hold any physical properties and it doesn't affect the results. Okay. Now I should specify the losses in the plate. Let's go back to electric problem and calculate the losses value. I'm going to use the contour tool, click to select the plate, open the integrals, and here is the joule heat in the volume. And I need to know the volume as well. 0.138 watts per 2000 millimeters cubed. In QuickField, you can type in not only the constant but also the equations. Millimeter cubed should be converted to the meter cubed, which is times 10 to the power of minus 9. And this equation I will copy and paste here in the conductor block label, volume power source. Okay. Again, before running the analysis, I should build the finite element mesh, mesh for edges, mesh for faces, mesh for volumes, solve all the problem files, and solve the problem. Open the results. And here you can see the temperature distribution. In fact, if you adjust the scale from 0 to 3, it's almost uniform temperature. 3.3 everywhere. Well, we had specified the uniform power density distribution in the plate, but in fact the power density distribution is not uniform. Let's go back to the electric problem. Here I will adjust the color grades, let it be 5. Let's divide the geometry model into sections. 5 sections will be, and for each section calculate its specific joule heat power density. To be able to do so, I need to open the geometry model. Let's put them one above another, switch to insert mode, and draw the boundaries of the color zones. Something like this. And this. And here. And the red zone is here. Okay, switch to Select Objects mode, select and remove unnecessary parts. Next, I'm going to run the simulation again to see how my artificial boundaries match the color boundaries. Build the finite element mesh and solve the problem again. Open the results. Again, adjust the field picture. The range from 0 to 200,000. And the color grades is 5. It seems I need to adjust the boundaries in geometry model. Again, let's put one window above another. Now this line should go somewhere here. This line should go there. And this line should go here. Okay, again, remove unnecessary parts. All these regions are in fact the same conductor, so these internal boundaries doesn't affect the current density distribution and the power distribution. Build the finite element mesh again and solve the problem again. Again, adjust the field picture, adjust the range, and the colors. For each region, you can see the specific power density. For this region, it is 0.2. For blue region, it is 0.6. For green region, it is 1. For yellow region, it is 1.4. And for red region, it is 1.8. Okay, open the thermal problem. You see it is based on the same geometry model, so we have the same, exactly the same boundaries in the thermal analysis problem. Toggle to the three-dimensional viewer. And here, instead of the label conductor, I'm going to assign different label. This would be red. This would be yellow. This would be green. This would be blue. And this would be dark blue. And for each region, I will specify specific joule heat power density. For the red region, it is thermal conductivity is 50 and the power density is 1.8 times 10 to the power of 5. For the yellow region, it is thermal conductivity 50, 1.4 times 10 to the power of 5 watts per meter cubed. For the green region, it is 1 times 10 to the power of 5 watts per meter cubed. For the blue region, it is 0.6 times 10 to the power of 5. And for the dark blue region, it is 0.2 times 10 to the power of 5. Okay. Now we have different regions with different joule heat power. Let's build the finite element mesh and run the thermal analysis again. Let's take a look at the results. Now you see that the temperature distribution corresponds to the power density distribution. In the narrow part, where the current density is high and the power density is high, the temperature is higher, and in the wide part, where the current density is low and the power density is low, the temperature is lower. The temperature difference now between cold and hot part is 1 degree Celsius. If you search for the temperature distribution in the conducting sheet, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the result pictures, and download the simulation files. Simulation files may be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition, that you can download from our website for free.